I want to welcome everybody also from my side. Again, Sven Mühlfriedl, a product manager at CryoBio1, responsible for cryotubes and biobanking tubes, for instance. So in the next 35 to 40-something minutes, I want to address sample storage tubes as quality critical components in biobanking. And I want to start with this slide, which describes biobanking as a challenge, and states that the ultimate goal, and I guess you as the biobankers, as the users may agree, the ultimate goal in biobanking being the maintenance of sample integrity and also the maintenance of high sample information over the entire process of the biobanking workflow. That means that starting from acquisition of a sample through storage and through release of a sample towards an end user, sample integrity and high sample information is high quality of sample information is a must. In order to address better why this can be a challenge, I wanted to explain briefly what the material and information flow in biobanking are. So the material flow is shown in this chart in the upper part of the picture. It starts with sample drawing. So we have a primary sample, which can be blood, can be urine, can be saliva or tissue. And later on, this is processed and aliquoted. And what we end up with after this stage of the workflow is a derivative or an aliquot. If, for instance, started with blood as a primary sample, a PBMC isolation may be a derivative of a primary sample. What is the central element of biobanking is the storage. It can last for days, weeks, months, but sometimes even decades. And especially the long-term storage over, let's say, 10 years makes biobanking quite a bit of a challenge because, of course, during this step, samples could potentially change, which you don't want to happen to a huge extent. Afterwards, samples can be retrieved, can be distributed, and can go to an end-user's lab where they can be analyzed for certain biomarkers or bioanalytes. Next to this material flow, there is also information flow. So when saying information flow, we think about sample information, processing information, storage conditions, and also analysis results, which all can be captured at certain stages and can be stored in a database. And sample management systems are, for instance, a means that is often utilized for this purpose. In the chart here, you see the red line in the center, which is the arrow of the workflow. Here it says sample tracking, and it's what we want to strengthen and put a focus on, namely that sample tracking is important. At any stage, you need to know what was the, let's say, number ID of your sample, and how does this relate to the information you have collected. And what is done very often today in modern biobanking is that a machine-readable code, a data matrix code, or a barcode is at this stage to do the machine-readable automated tracking. And the example here, you see a CryoBio1 biobanking tube, and on the bottom you see the black bottom portion with the white mark on it. This is the data matrix code, and this allows for machine-readable tracking. And this brings us immediately to the challenges now. They can and be part of both sides of the material flow and the information flow. What can happen basically is that you have maybe a too long or inappropriate sample processing, or your choice of your storage vessel or storage temperature is not really what it's supposed to be. All this can lead to low sample quality and finally degradation, alteration of your biomarkers in your biospecimen. What can happen is that there is an incomplete characterization of your sample at the very beginning. Later on, you will never ever fill in this gap. There can also be poor accessibility and searchability of your info of your database, which makes your approach very unattractive for end users because they want to get rather comprehensive information about the samples you have. And finally, there can be problems with sample traceability, and this is an absolute problem because if you cannot trace your sample anymore, then it's actually lost and gone. I want to spend one slide on storage temperatures and what can be recommended here, and then we can use these slides to come to the conclusion and the actual topic, what makes a good biobanking tube. But before that, a few words on storage temperatures. On this slide, you see to the right-hand side a liquid nitrogen tank. It is opened so that you can see the area. Many of you are familiar with that. There's a liquid nitrogen lake down there, and above there is the vapor phase where a temperature gradient is formed. At any side of this gradient, you have temperatures below -130 Celsius, which is the glass transition temperature of water, and which is, to our understanding today, temperature that is good for keeping samples unaltered for very long, because life processes are standing still and viable cells maintain their viability at this temperature. And this actually, this temperature below -130 degrees Celsius is today regarded as a gold standard. So biobank can apply such storage conditions is optimum. A lot of biobanks today are run at -80 degrees Celsius. This is also a good standard. There is, though, some evidence that even at this temperature, some biomarkers may change, but still, to our current understanding, it's a good compromise to store at -80 to at least keep your samples in a decent state. What definitely should be avoided for liquid samples and also for frozen fresh tissue is storage at -20 or higher, because there would definitely alteration of your samples occur. An exception at this stage is paraffin blocks with tissue in them, which can be stored at room temperature, but this is a rather rare situation in biobanking. So I talked about the challenge of biobanking, the workflow, and the things that can go wrong, and the extremely low temperatures that are recommended to store your samples at. This brings us to a slide which lists the requirements we can deduce from everything we have talked about so far, and will lead us to a good biobanking or storage tube. Here you see an example of such a tube, and the things that a good tube brings with it, for instance, a compact design. You want to ensure that your sample is taking up storage space, but your tube is taking up as little as possible, because you don't want to store like plastic in your biostore, but you want to store a sample. Here we see an example of a very compact tube, and this would allow for optimum usage of available sample storage space, and this can also allow for cost reduction and for running your biobank on a very positive cost basis. All the other things are listed here are related strongly to the title of this presentation, namely to the quality of your biobanking approach. The first one was a bit more cost associated, but everything that's coming now is quality related. The first point is the tube must be resistant to extremely low temperatures. There's nothing that needs to be added. We just looked at temperatures. We stated -80 and even -196 are storage temperatures of interest, and this challenge is given, and the tube should simply fulfill this criterion. But it is challenging to the material and also to the closure of the tube. In addition, the tube should be automation friendly, and also in the rack should be automation friendly combination of labware. A lot of automation friendliness is about the dimensions of the racks. They should come in standard formats, which we will see in a minute. But it's also a lot about the cap of the tube. The cap should be deeper friendly. It should be possible to open it with devices. The cap of the tube should close very tightly, and this also at low temperatures, and this also over long periods of time, in order to make sure that you are not losing any water content from your sample. The raw material of the polymer or of the tube should be of high quality. It should be pure and should not contain a lot of unintended or unwanted additives. There be, in the best case, a machine readable code, a tag on the bottom of the tube, which allows for tracking, which is robust and which provides a unique identifier for tube identification and traceability. I think that automation compatibility is something that can add quality to your biobanking approach, because if you are capable of using automation, you can speed up your processes, you can have a better throughput, you can have less processing time, and this is in any respect positive for the preservation of the original composition of your, let's say, sample or a serum or blood sample. Here you see two examples of automation compatible RAC formats. In the picture to the left, you see SLA ANSI standard compliant RAC format. In this case, it's a 96-way layout. These tubes can accommodate 300, 600, or 1,000 microliters of liquid sample and come in the standard format that I just mentioned. In the lower picture to the left, you see again a standard format compliant with the ANSI and SLAS standard, but here it is a 48-way layout which allows for storage of larger tubes. They are larger in dimension. These tubes can accommodate 1, 2, or for example 4 milliliters of solution. So it's standardized about these two different racks. Is their height, of course, as you can see in the picture. They are all different heights, but standardized is their footprint, is the width of the rack, also the length of the rack. In particular, the dimensions that you can find in this standard are 85.48 millimeters width and 127.76 millimeters in length or depth. If such standardized rack formats for your labware, for your biobank, they are prepared for a whole universe, let's say, of automated processes which you could theoretically apply. This is available to utilize this rack format, and they carry out processes such as decapping and recapping, pipetting and aliquotation can be done with these devices. Then derivatization such as nucleic acid extraction can be done. Picking of tubes from racks can be done in automated systems, and also the re-arraying of tubes. So you have two semi-full racks, you can rearray the tubes so that you end up with one complete rack. Also for the process, automates are available. This introductory portion of my presentation, I want to conclude here with a few key points. Demands for high quality standards in sample and information management. State-of-the-art sample tracking can be achieved with machine readable codes. There are automated equipment available and be utilized for all kinds of processes in your biobanking approach and workflow. And if you want to utilize such equipment and take advantage of its existence, then it is recommended to commit to standardized rack formats which are available in 48 and 96 way layouts. The standard we talk about here is the micro titer plate standard, or also called officially the SLA as ANSI standard. After the introduction, I want to move on with a few slides, some more insight into concepts for tube closure. And what you can see on the chart is different ways of closing a tube. So on the left-hand side, you see the approach of heat sealing with a foil. And in the center, you see a silicone, or we also call it push cap. And to the right, you see a little cartoon of a screw cap, which is meant to have a thread and is really screwed onto the tube. The heat sealing approach is an interesting solution. application. It is but only single use because if you have heat sealed the foil onto your array of tubes in your rack, then if you open them afterwards, you peel away the foil, you cannot close them anymore. This is not reversible, it's single use. However, for many biobanks which for a single aliquot hypothesis or philosophy, it works because you only need to close and open one time. We also did tests with this approach and we found it only recommendable for -80. We did not find it work in environments in vapor phase above liquid nitrogen. The shrinkage rates of the material at this ultra low temperature seem to be too different between foil and a tube, so that you still produce a good seal or a tight closure at this low temperature. The center I said is the push cap or the silicone plug, also possible to be used for closure of biobanking tubes. This is a rather common and widely used system. It is reclosable, so this is one feature that is added now. Still, it's only recommended for temperatures down to -80 degrees Celsius. The seal you would form here is, however, not the exact same quality as compared to a screw cap, which is producing the best seal and is therefore also recommended for long-term storage. As I said, we find this type of tube on the right-hand side. It's reclosable, it is suitable for any temperature, and this is also suitable for air shipment. The type of screw cap, together with tubes, comes from many suppliers with an IATA certificate, so from Greiner Bio One, and this IATA certificate certifies the product to be suitable for air shipment of samples. And it's a rare situation that samples that are leaving a biobank need to be transported via air freight. So this extra feature you are gaining with the screw cap is, we believe, an important one. If we talk about screw caps and their advantages, it's not finished because even screw caps can vary and there are different types available. But they fall into two categories. One is screw caps with gasket for internal thread tubes. The gasket material can be silicone or thermoplastic elastomer, and you see an example, a little cartoon or drawing of such a screw cap on the upper picture. The lower picture shows a different type of screw cap. These screw caps are without gasket. They form a seal not by using flexible material, but by pressing polymer of the screw cap against polymer of the tube and therefore forming a barrier and a seal. These screw caps are often used for tubes with external threads. There was a lot of discussion in the community going on. There could be any regulation be drawn or provided in terms of what is a good screw cap for which type of application. So it was also a lot about long-term performance and performance in the very challenging environment of vapor phase liquid nitrogen. So first set up a benchmarking study where in total 9 different tubes from different suppliers have been tested. Filled these tubes with working volumes of water. We put them in the appropriate racks taken in, and we stored them in the vapor phase above liquid nitrogen for 150 days. What we've seen is differences in the amount of water we could recover after thawing the tubes after 150 days. It wasn't real recovery, it was more that we weighed the tubes with precision scales. We made sure that there is no interference with false positive or negative positive results because of water condensating on the surface. So we made sure that we are not biased in this assay. And what we have done is we have tested the several tubes and we have clustered them in groups depending on which type of screw cap they are using. First group we tested and which shown here contained 2 different brands from 2 suppliers, and these were both externally threaded tubes. The second class of tubes contained in this experiment 5 tube brands. They were all internally threaded tubes and they used a silicone gasket. And the third group was internally threaded tubes using a TPE gasket in their screw cap, and 2 brands have been tested here. So what you see in the chart is we discriminate between 90% or 100% of retained sample volume. 100% of course is perfect. If a tube can deliver such a result, you are on the safe side that even after long-term storage and in the challenging vapor phase condition, your sample volume will be retained. So see here is best and worst performance and also what is in between. For the externally threaded tubes, we had a little of a biased situation. The best performer was pretty good, but worst performer was not performing very well. This tube had already lost 10% of its sample volume after half a year. It's a thing to us that the lack of a flexible material is still a bit challenging if you want to really form a tight seal, because any tiny little deviation of dimensions or of material from its how it's supposed to be situation versus how it is a situation cannot be equilibrated with any flexible material, and you can see it as a leakage problem or evaporation problem. The 2 other groups of screw caps, both cases externally threaded screw caps for internally threaded tubes, they come with a flexible material and they yield pretty good results. Intriguing or thing is that the silicon class has the most narrow variation, and all the tubes we have tested there, all the 5, yielded pretty good results. We found Greiner Bio1's biobanking tube the best performer in this group. Taking together the story about the tube and the screw caps, I want to suggest these recommendations. We suggested screw caps with gasket for internally threaded tubes are a good solution if your aim is rather long-term storage and you have the capability to automatically close and open the tubes. There's not much handling, manual gripping surface here, but if you use semi or fully automated devices for closing the tubes, you have a very good solution. If on the other hand side, it is more about manually opening and closing the tubes, the other version of screw cap for the externally threaded tubes is a good solution. However, be aware that if you store really long, let's say you aim at 5 or 10 years of storage, this may be not your preferred solution for labware. Slide, you will see a movie. Not running yet, now it's running. In this movie you can see a device from the company Hamilton Storage. This is a fully automated decapper. The decapper opens tubes in 96 but could also be 48-way racks. It does it always in this case twice, so 12 tubes are opened at once and then the screw caps are unscrewed and they are put down in 96 well plates which serve as a cap carrier in this device. Once the tubes have been opened, you can do your aliquotation or whatever, and then the screw caps can be reapplied. As reversing the process, this is what you see right now. We can go to the next slide, where you see an alternative solution. It is a more or less expensive solution. Please forgive us that this video has some sound which is not very nice, but it's just a natural sound. But what you can see is that it's the same principle. You can open 8 tubes at once. You can put the screw caps down in a 96 well plate. The only difference is that here you manually operate the device. It's a handheld device, but precision and the result of a precise closure is the same. And again, a bit less of an investment if your biobank is seeking for a solution for a bit less throughput and which is also less expensive. In summary, assisted tube closure is recommended and it leads to less processing time, which is better for your samples. It leads to more precise closure and also better long-term tightness. These data are not shown here, the long-term tightness, but I will later on refer to a piece of literature which Greiner Bio 1 has recently launched and published, and there you can get more insight and even find these data. The conclusion in total is that screw cap tubes are suited for any temperature of storage and also for any duration of storage, plus they can be used for freight sample shipment. Screws follow different designs with different sealing mechanisms. Internally threaded tubes with silicon gasket provide a very good seal with very low evaporation in long-term storage tests in vapor phase above liquid nitrogen. Finally, machine-assisted tube closure is a good suggestion for medium and high throughput because it reduces processing time and it adds reliability of the quality seal you are producing when closing the tube. So after this chapter, I want to dive into a bit of different matter, which is raw material, additives, and cleanliness of your tubes and your sample. Put together some requirements here. They are on the left-hand side, and some consequences which are, I think, worth being addressed and known. First of all, everybody would agree that tubes must be free of biological contaminants for most biobanking applications. The consequence is that from the beginning on, you keep your tube production clean as possible. What you do is you produce tubes in a particle-reduced controlled environment, and you do this in combination with frequent testing for endotoxins, DNA, DNAs, RNAs, so all biological contaminants which are known and which should be strictly avoided in this context. On the other hand side, you want to also make sure that no non-biological substances, chemicals, are contaminating your samples. So it should not contain additives that are migrating from the polymer into your sample. And especially if you think about long storage periods, such migration could happen because there's a lot of time given, and they could finally change the composition of your biospecimen. What we do today is we apply and use for tube production polymers which are of high quality and with a good certification. A certificate we try to use at this stage a USP Class 6 certificate for raw materials and products in accordance with the US Pharmacopoeia. It's a rather strict test about biocompatibility of raw material and or products. And this test, again, tells us if something is biocompatible. It's more from medical applications, but it also tells us if something is biocompatible and it passes this strict test, it's also very likely that it has a very low content of additives that could leach into a sample. Also should be done is things that are not really needed in the context of polymers and production of such tubes should be avoided. And one example we have chosen for this webinar is a class of substances which within the injection molding industry are well known. We call them mold release agents. You can avoid these substances. Greiner 1, for instance, is absolutely not using them in production processes. And on the next slide, I'll give you some insight that this is a thing that is important, and it is obviously also a matter which is today not standardized, and you find different qualities on the market here. But before we come to this point, I want to address one third important requirement, and this is that we have to make sure that a tube made from a raw material, certain characteristics which maybe are also proven in tests, that this becomes or will stay available over the next years, so that anybody who has committed to a certain lab area and maybe even integrated it into an automated environment, that these users can take advantage of the same tube quality and design also during the next years. And if we think back that raw materials can be discontinued or can be changed in their composition, this can become rather critical. A solution here is another kind of label that raw materials come with. And this label is the label medical grade polymer. It's used by polymer manufacturers, and it suggests and also providing evidence that the raw material has a long history, that cleaning procedures and other measures are taken, so that there is little chance that the raw material with the given composition can be mixed up with other batches of raw material, maybe even other subtypes of raw material. And also there's a certain commitment of the supplier to the customer, in this case the manufacturer of the tube, in terms of future availability of the raw material. So if there's a plan to discontinue the raw material, then the customer, the producer of the tubes, will be noted or notified in advance, something like 2 years or so, so that an alternative material with identical properties can be found. So I mentioned mold release agents as one type of contaminant or additive one can be confronted with if one uses labware-made polymers. And what you see here in this little cartoon on the right-hand side is an injection mold. It's, of course, simplified, oversimplified. The gray portion is the actual injection mold. And on the left panel, you see the mold being closed. There is a wide area, a cavity in between the inner portion of the mold and the outer portion. And this actually an opening, a cavity, a hole, which is the exact shape of the future tube. What is going to happen is that melted hot polymer is injected into the injection mold. It gets hard, and what we then have is the actual product, the storage tube, still sitting in the mold. And what then needs to happen is what we call demolding. The mold needs to be opened, the tube needs to be pulled out of the core of the mold, and we are done. And this pulling out or taking out of the product out of the injection mold can be sometimes challenging if design of mold and product and tube are not really matching very nicely and are not done in a clever way so that they allow for injection molding and demolding. A trick at this stage is that you just spray some lubricant or slippery substance onto the injection mold, or you do the injection molding, or use the raw material which has the slippery agent in its polymer structure. So both of these things, either spraying onto the mold or having it intrinsically in the polymer, can help demolding and can make manufacturers' life much easier. But they bear the risk, of course, that these substances could diffuse into the stored sample. So there is at Greiner Bio a strict rule to not use these injection molding release agents. And we were just interested to see how storage that are available today perform, and if there's a sign of some of these tubes being contaminated with such substances. The actual substance can vary, and there's a lot of mold release agents available today. So we went a little bit along the indirect way. We just said amide is the substance class, chemical substance class, in which you find most of these mold release agents. In other words, most mold release agents are amides. So we extracted tubes with solvents over several days at defined conditions. We have then examined the extract. We have taken it out of the tube and we have examined it in infrared spectroscopy. The idea was to look for traces of extracted substance that was extracted from the polymer by usage of the solvent. And we have focused on wave number bands in this infrared spectroscopical analysis, wave number bands which are indicative of amide being present. Amide is a good candidate here to look for because it gives clear signals in infrared spectroscopy. And we found, and we have tested several tubes, that indeed there were some candidates which showed a signal, and one of them, an example is shown here, it's the upper curve, shows a very strong signal. So this is evidence for the fact that most of these agents are still used today. There is no regulation to not use them in some context. We suggest in biobanking context it could cause problem for samples which are liquid, for samples which contain dissolved biomarkers, and for samples which later on go into a biomarker assay, and that such types of substances can interfere with analysis. So this slide is meant to strengthen the awareness for users that not every raw material quality is the same, and that depending on the biobanking approach and what your aim is and what your sample type is and what your whatever endpoint assay is, you'd make an aware selection of a tube that suits your requirements. The same is true for unwanted and unintended binding of biomarkers onto tube surfaces. It's the same thing. There are differences, as you will see in a minute, and the idea is again to sharpen the awareness for these phenomena, so that if there is rare biomarkers which can be in your samples and they are of importance, then maybe an appropriate choice is of importance. In order to understand if such unintended biomarker adsorption occurs, we have developed the following assay, which is shown in the picture under A, B, and C. The assay works in the following way. Tubes from different suppliers were taken. Material sample, which is disc-shaped and all at the same dimensions, it was standardized, had been pushed out of the tubes, and the material sample has then been incubated with a mixture of serum and IGF-1 spiked into the serum overnight at minus 80 degrees Celsius. It was that the IGF-1 that was spiked into the serum, which was used for this incubation step, was radioactively labeled, so that later on it could be identified if it had bound onto the surface of the material sample. On the other day, the frozen sample was thawed, the lid was removed without any remaining rest, and the material sample was then put in contact with scintillation liquid, and it was met and assessed if residual radioactivity was present. In this assay, we had a standard curve so that we could recalculate from certain counts per minute radioactivity how much IGF-1 from the original serum was actually captured on the surface. We tested in this assay two different tubes. One of them was from Greiner Bio1, which are sold as sterile tubes. They are irradiation sterilized using a validated procedure. And we have also tested 4 tubes, one again from Greiner Bio1, 3 tubes from other suppliers, and these tubes were sold as non-sterile tubes. They were DNase, endotoxin, RNase free, but they were not undergoing any irradiation-based sterilization procedure. What we had in the class of sterilized tubes, the first 2 tubes, was a bit of a surprise, because we saw that 12% of the IGF-1 that had been spiked into the serum, making a rare biomarker situation, the 12% of this IGF-1 was actually captured onto the surface of the material sample. In the case of non-sterilized tubes, the situation was better. Here only 4 or 5% of the IGF-1 was captured. With the exception of one tube, it's the third from the top. It's the first in the class of non-sterilized tubes. And the tube bound almost 18% of the IGF-1 presented to the material sample. We found a bit of an alarming finding. We drew a conclusion. The conclusion is that non-sterile tubes, but again these tubes are certified endotoxin, DNase, and RNase free, should be used for liquid samples, which later on are used for biomarker analysis, as sterile tubes should be used for cell storage with the aim of later on cultivating these cells in cell culture. Also, some pharma accounts or some GMP-regulated environments may ask for sterilized tubes. Then, of course, these tubes should also be utilized. And as I mentioned before, the idea here is to develop a better idea what is a good recommendation for each type of application, and it would also be interesting to assess how other types of molecules, IGF-1 is a small peptide, there are lipid substances, there are polysaccharides. It would be interesting to see how these substances behave in this test, and there may be more research going on in the future. So on the next slide, I want to explain one more time how I have to just check. We are on the right. Yes. I want to again explain the difference between sterile versus non-sterile tubes. So tubes that are produced and sold as non-sterile, they are produced in a particle-reduced and particle-controlled clean room-like environment under hygienic standards, and this is done in combination with frequent monitoring, so it can really be secure that what you aimed at, namely no contaminants, is really the case. Tubes are clean, but not carrying the label sterile. Part of tubes are then taken and sent to sterilization facilities where they undergo E-beam or gamma or X-ray sterilization. Greiner Bio1 uses E-beam for these cryotubes only because it's a very gentle to the material approach, but not gentle to any germs that could be contained. We validate this process and we guarantee a sterility level of 10 to the minus 6. These products then are sold as sterile products, good for cell culture applications and wherever sterile quality is needed. I want to summarize this part of my presentation, which was dealing with the raw material cleanliness and also types of contaminants. Cryotubes should be made of USB Class 6 certified materials in order to assure biocompatibility and purity. Cryotubes should be guaranteed free of endotoxins, DNA, DNAs, and RNAs. Cryotubes should be made of medical grade material with assured long-term availability. And non-sterile cryotubes, which are free of biological contaminants, are recommended for liquid sample storage, whereas sterile cryotubes, which are undergoing validated irradiation-based sterilization procedures, are recommended for storage of cells or organisms for subsequent cultivation. In the last chapter of my presentation, I want to briefly talk about machine-readable codes that can be used for tracking of samples, and as the title suggests, since they are machine-readable, they allow for automation and error-proof identification of individual tubes. You see two examples here. On the left-hand side, a 4 milliliter cryotube with a linear barcode. Linear barcodes are one option here. On the right-hand side, you see a biobanking tube with a data matrix code. That's the other option that is used today. Matrix code is a little bit more the modern standard. It reveals several advantages over linear barcodes, which you will see in a few minutes. Here you just see how such a code is composed, exemplified based on a Greiner Bio1 biobanking tube. You see a magnification of the bottom portion. There you see the actual code. What Greiner Bio1 added as a feature is human readable text surrounding the code. It allows for identifying, reading the ID information which is encrypted in the actual code. In this case, it's GH011121639. This number starting with the G is a unique identifier, and if you order such a tube off the shelf from a warehouse, then it's kind of guaranteed that there is no other tube from Greiner Bio1 that has this code. So there is a 100% guarantee that you have a unique identifier on your tube when purchasing from one supplier, in this case Greiner Bio1. In the center between the lettering, you see the actual code. It has a finder pattern, an L-shaped curve, and a dashed line. These two just together we call finder pattern. They role when a scanner needs to find symbols and find out about their orientation, and or to be ready to decode their content. The actual content is then encoded the central portion of the 2D code, which you see in this picture and it looks like a checkboard. So slide, there are several advantages of data metrics codes over linear barcodes addressed. The metrics code provides a higher data capacity, so the ID numbers, identifiers can be longer, can be more complex. There's the capability to scan multiple codes at once if they are presented in an array. This is not possible with linear barcodes. There are better algorithms for error correction. The readability of partially damaged codes is given and illustrated and exemplified in a picture down there. So what we have done is we have reproduced one and the same code 5 times, and we have on purpose damaged the code without needle, so that part of the code was gone. What you see here is that the more you change the code, okay, you cannot see it here, but it's the case, the more tricky it's for the scanner to read it. You sometimes have to give it a second chance or so, but it succeeds to read the code up to an areal damage of, in this case, 22%. Even some codes that are destroyed to 25% are still readable. Of course, there's a limit. If you exceed the limit, then it's not readable anymore. Here you see an example on the right-hand side of a code that is destroyed to 40%, then it's not readable anymore. But the end of redundancy and error correction is superior. It's not given with linear barcodes, and it speaks for data metrics codes as a future-oriented solution for automated ID and tube tracking. I want to conclude this last chapter of my webinar. Linear barcodes and data metrics codes are machine-readable codes. They are utilized for fail-safe, efficient, and unambiguous identification and tracking of samples and biobanking, as data metrics codes combine a few advantages over linear barcodes, and amongst them are high data capacity, improved error correction, and bulk readability of multiple code at once. So I want to list the tube requirements for storage tube for a good biobanking approach. Sample processing, we can deduce that tubes must be compatible with automated equipment for tube opening and closing, because this helps you with your processing time and the throughput within a given time. All standardized racks should be utilized because they allow for automated processing, not only in the or at the stage of decapping and recapping, but also if it comes about aliquotation or processing of samples. During sample storage, there are a few things that can really challenge your storage tubes, amongst them very low temperatures, and also the need to form a tight and good closure and seal so that no water content is away and leaving your sample tube. There should be as little as possible additives leaching from your polymer into the sample. There should be no contaminants, I mean biological contaminants here in the tube. There should be a low absorption rate of biomolecules onto the tube surface, and the tubes should be, of course, compatible with the storage equipment, especially if we think of automated equipment again. If it comes about sample distribution, it is important that the tubes are closing tightly and they also withstand the critical pressure conditions that you see in air freight, transportation, and shipment. And finally, throughout the entire process, there is sample tracking taking place. It requires a unique, machine-readable, and robust data metrics code in each tube and also on each rack. As mentioned earlier, published a white paper this year, which is available from Greiner Bio 1. It can be ordered as a reprint under the part number given here. It can be also downloaded from our homepage, or you can just approach your Greiner Bio 1 sales representative or other distribution partner if you want a reprint of this paper. The title of the document is the same as the title of this webinar, Sample Storage Tubes as Quality Critical Components in Biobanking. It's our forum white paper number 21. And in this document, you find all the experiments we have talked about, but what you find here is many more details about the raw data we had, about procedures, how we have tested everything, and there's also additional tests detailed and provided in this document. Yeah, and with this, I want to thank you for attending, and we would be very glad to take your questions now. And with this, I will hand over to Roger.
Thank you, Sven. Their time, we had 50 minutes. We received quite a few questions, so thank you for those who have sent questions in. We're not going to be able to attend to all those questions, so let's go 4 or 5 of them, and then the others will have to respond to you via email or phone call after this event. The first question for you, Sven, how do you explain sterile tubes binding more IGF-1 than sterile tubes as shown in your IGF-1 absorption assay?
So, as I said, in most cases, or actually in all cases, irradiation is used to sterilize tubes. It can be E-beam, gamma beam, or X-ray. This is highly energetic irradiation. It modifies the polymer and also its surface. What, for instance, can do is it can oxidize the surface. It can introduce hydrophilicity on the surface. Many biomarkers are having an affinity to bind to hydrophilic residues, such as IGF-1, and this can explain, so the modification of the polymer and the surface, mechanically and chemically, can explain that irradiation causes higher binding capacity of the surface.
Okay, thank you. Question 2, is there data for the non-specific absorption of molecules besides that of the IGF-1?
So I think I mentioned it briefly that so far IGF-1 was done, and other classes of molecules may be different. We haven't done much in IGF-1 so far. We are planning to do more, and we would find it very interesting if maybe also amongst users, but also from us, more data would become available, so the thorough choice can be get in the future a tube which is suited for whatever the goal of the individual biobanking approach is. We have tested genomic DNA, which has not been shown here. Genomic DNA didn't bind much. We only found very little binding. It was in the picogram range, and we also didn't find huge differences between sterile and non-sterile. So if the plan is to store genomic DNA, it should be not critical.
Okay. 3 is a long one, so let's do it. My bank collects and stores samples from collaboration partners all over the world. We have these samples in all kinds of 2D coded storage tubes from different suppliers. A way to make sure that the 2D coded tubes from our collaboration partners do not come with code duplicates. Because each tube should carry a unique identifier. Is that possible?
There's no agreement or norm or whatever between the different suppliers, so that it can be secured that not another supplier is using a code that we, for instance, as a Greiner Bio1 are using. Our codes, if they are off the shelf and non-customized, they start with the letter G. There comes a number, but we can secure that not anybody else is using this. We can, though, secure is that if you buy Biobanking or a cryotube or any barcoded product from Greiner Bio1, we can secure that there will be no duplicate code be used, because we have entire control over all the barcodes we are using. We have databases generating unique barcodes. So this can be guaranteed, but it cannot be done between different suppliers.
Another question. How is that Greiner Bio1's manufacture does not require mold release agents?
So here it is, I would say, experience and also knowledge about how to design a product. For instance, in this case, a storage tube. They're good for injection molding as a manufacturing process. things you have to be aware of and you have to take into account, and then you can design a tube which can be released out of a mold without the need of anything that is slippery or so. So experience, and it is also, let's say, kind of a product which suits the needs of injection molding as a manufacturing technology.
Perfect. I think for now, how is the data matrix code quality rating ascertained?
During the production process, there is a 100% in-process control for the readability and quality of all the data matrix codes. This is against the AIM standard. It's the Automatic Identification and Mobility Standard. It ranks the code quality from A to H, and A are the best ones, and D are the only ones that are allowed to leave the factory. Everything else will be discarded. In the benchmarking study we have done, we have applied something different, namely ISO norm. Cited in the paper, it's very, let's say, stringent and strict norm, and we have done this in combination with the barcode validation machine, and in our forum number 21, we show how also data metrics quality can vary, and we give some more insight into this. So it's different standards we are actually applying.